es igual, usaré el boli. Déjalo, uso el boli.
Sí hay. Bueno, presento a Damián Gomila, que es un investigador del ICISC. Él es licenciado en física por la Universidad de Barcelona, hizo la tesis en la UIB, la Universidad de las Baleares, luego estuvo de postdoc 3 años en Glasgow, luego se incorporó y entonces éramos sin idea, éramos un instituto conjunto. Y en el 2012, ¿no? Desde el 2012 es investigador titular, científico titular del CSIC en el CSIC. Y bueno, su expertise es en física de sistemas complejos y en particular trabaja con formación de patrones en ecología y en sistemas ópticos, ¿no?
Sí. Diversos.
Y bueno, hemos colaborado en algún trabajo y bueno, espero que continúe la colaboración y nos explicará pues, todo este trabajo en emergencia de patrones en Colombia.
Thank you very much. So I'll continue in English. Well, it's a great pleasure to give this talk here, Daniel. So I'm very glad for this collaboration. So I'll talk about pattern formation in Posidonia meadows today, and particularly this thing called faded circles. It's a bit mysterious. I'll explain in a while what this is. Well, I'm Damián Gomila, and the work has been mainly done, and also nice slides I'll show by Daniel Ruiz, who is sitting over here. He's a student. He's the one doing the hard work on this topic. And it's in collaboration with Tomás Sintes, that's some of you know, and Emilio Hernández García. We are all at the FISC. And then with Nuria and Carlos Duarte, which is in Saudi Arabia. Okay, so let's start. When I give this presentation to physicists and mathematicians, I spend sometimes talking about what is Posidonia and the importance. So I think here I can skip this altogether, because you know why this is such an important ecosystem and so on. So I go directly into the matter of what I want to explain. And what I want to explain is that when you look into the Posidonia meadows, you don't see an homogeneous thing. So you see a great detail of spatial structures in the spatial distribution. And this is a picture of Cabrera. And that I saw this picture first in a talk by Tomás, who did a model of Posidonia that I'll mention later. And what you see here, you see that this is a Posidonia meadow, and you see spots, you see gaps, circular gaps, and also spots, and the surface is very. So that's something that already catch my attention, and also this was observed also somewhere else in the Adriatic Sea. More recently, that you see also is very faint, but you can see them. There are sort of circles, more or less along the coast. Where this is a gap, so this is no Posidonia. That's bare soil inside the Posidonia meadow. So there is something going on there. Okay, this actually was mentioned in the press. Because when you see a circle in a wild setting, why is there a circle there? And all sort of strange explanations, and in particular, maybe it's military experiments. And actually, it makes sense because if you throw a bomb and you kill Posidonia in a certain range, since it grows so slowly, that gap will stay there for some time. So could be, and here also, illegal fishing with dynamite, and I will not go into the extraterrestrial observations, okay? So I'll skip that. Although I put Star Trek movie now. So the explanation I thought when I saw that, because I've been working on pattern formation for many years, I thought that's pattern formation phenomenon. So we should look into that in detail. And that what is pattern formation, and in particular I want just to say a few words. You may already have heard this, what has to do with complex systems. So as a matter of fact, this talk is about, I'll explain you as a physicist, I'll talk about the Posidonia from the point of view of complex systems, not as a biologist, but as a physicist. And so what is a complex system? I used to explain in that sentence there, but any Star Trek fan here? No, not really? I'm a very fan of Star Trek. This is Lieutenant Commander Data. There is an episode where the Enterprise, which is the starship, starts to behave strangely. It looks like as if the Enterprise, so the starship, starts to make decisions on its own. No? Starts to behave strangely. And they look for an explanation, no? Like in the case of the seagrass. No? And Data, which is an android, comes with an explanation in terms of complex systems. No? Just 1 minute. No?
Complex systems can sometimes behave in ways that are entirely unpredictable. The human brain, for example, might be described in terms of cellular functions and neurochemical interactions. That description does not explain human consciousness, a capacity that far exceeds simple neural functions. Consciousness is an emergent property.
In other words, something that's more than just the sum of its parts.
Yeah, that's it. No, it was very nice to see it in an episode. No? So that's the essence of complex system. No? So you have many interacting units. Data was talking about the neurons. No? You can study neurons, but studying a single neuron, you will not understand consciousness. No? So you need to study the complex system. No? So as a result of these many interaction units, you get this emergence or collective behavior, collective phenomena, no? as a whole. Okay? And this is everywhere in nature. And this is, for instance, a block of birds. So you have one bird, a few birds that already make a formation. But if you have many of them, okay, you have a flock of birds. Sorry, you have a flock of birds. Well, you have seen this, no? That's dramatic. So you see the dynamics of the flock is very complex. So they form all these sort of structures. You cannot understand that dynamics studying a single one. It's the interaction between them that makes that. Okay, so that's complex. That's an emergent behavior. Okay, and we at the IFISC study this from all sort of point of views and systems. No? And for instance, some people there study also that. So the society as an emergent phenomenon from the human interactions. No? That's social behavior. Okay, so from this perspective, I want to study Posidonia also as a complex system. No? So there we have the units. You think of Posidonia of the shoots, no? And then you have interaction. No? And I have to talk a little bit about plant interaction. That probably you know more than me. Okay, so I may say some naive things, but nevertheless I'll go on. So I'm plant interaction. This is my backyard, and this is an almond tree that, well, it's not an almond tree. It has been grafted with prune. No? So it's a prune tree, which are very well adapted to the drought conditions in Mallorca. No? So it's a species which is very well adapted. It was very nice. It was very nice prunes. And my neighbor planted these guys here, which are this to make a vegetal fence. No? So they planted to make this fence. She didn't cut it very often, as you see. It's huge. So after a couple of years, she planted this. This guy died. No? And why is that? Well, I don't know for certain, no, but my explanation is that she was not watering it a lot. Okay, so probably these guys, which are very strong, are just sucking the water out of this. And if it was isolated, it was able, with the remaining water during all summer, to go to pass through the summer. When these guys took the water, it had not enough water, and it just dried. Okay, so that's an example of interaction through this would be in terrestrial plants, the competition for water. No? So, and in this particular case, well, I'll use it as an example because this has been studied quite a lot. And I'll say a few words about this before to go into the Posidonia. So this interaction gives rise to a phenomenon which is called a modulation instability, or also called as Turing instability. This Turing is Alan Turing, the one of the computer. Okay, he studied embryo development and how the cells as they grow, they get patterned, no? And they study these models of pattern formation. No? That's why it's called Turing instability. So you have a meadow, or you have many plants, and this will be going down. We are increasing the mortality. You can think of reducing water for terrestrial plants, for instance. So you have enough water, enough resources. You have an homogeneous cover, and it's fine. Every plant has enough resources to survive, to live. Okay? But then if you reduce, think of reducing water income, maybe in this case. So now I put it a little bit smaller, right? So it has less water, it's a bit smaller, but still all plants can survive. Maybe. No? Now let's focus on one of the shoots. maybe this one, no? And this shallow area here is the region where maybe the roots or whatever is able to take resources in all that region, okay? So non-local, no? Has certain extent of interaction, no? So if the resources now are very scarce, so you are at the limit, just at the limit where you have just enough for everybody, but a little less would die, okay? So you have the homogeneous cover is fine, every plant has just enough to survive, okay? But then think of maybe the case where there are some here that incidentally they die for whatever reason, no? So they free some resources here, okay? So this plant here, this guy here can take the resources and grow a little bit more, okay? Because it has more resources, so it grows a little bit more, no? And then you get a bit taller here, right? But since this is larger now, or there is more density, it's taking more resources here. Because it has grown, now it has taken more from here. So now here, there is not enough for the plant to grow again. If a seed comes here and wants to grow, has not enough water because this guy is taking it out. Okay? At the same time, he's also taking it out from there. So since this guy now is stronger than this one, and is taking resources from here, this now has not enough to survive. And this will make this die. No? So in the next step, what you have is that these guys will die here, and this grow because take the resources along. See? So as you reduce from an homogeneous cover of vegetation, you reduce the resources, at a certain point, there is an instability. And the homogeneous cover, even if it could survive because it has enough for everybody, is unstable. Because if your neighbor takes a little bit, you die, and it grows. And this creates this modulation. Okay? And this is called the modulation instability or Turing instability. And this leads to a pattern. Yeah? You follow? So, and this is because of the interaction. This is because of the interaction. So the next question would be, think of this very nice land, no? This Greece football court, whatever, no? It's lovely, no? And you have enough water, no? And you, for some reasons, no? Global change or whatever reason, the water income starts to decrease, no? And you get that phenomenon, you get the modulation instability. Some parts will start to die, and others will use those resources to survive. No? So the question is, which pattern will arise? Which will be the outcome of this instability? No? And that's what I want to explain today a little bit. Okay? And for that we can, let me do another thing now. We can have a look at and I make use of Google Maps, which is lovely. Okay? Because here well, that's the world, of course. And in the world you have this phenomenon, which is, well, you have a gradient of water income from the equator to the tropics, right? So at the equator you have a lot of water, a lot of rain, a lot of water, a lot of resources. The vegetation cover is dense, is homogeneous, let's say. No? As a matter in a rainforest, as a matter of fact, is very very dense, no? And they actually compete for light, not for water. No? But that's another issue. As you move north or south, never mind, you got above the tropics, you got the desert. So very little water income, no? And you have here no vegetation at all. Okay? Somewhere in the middle, you have just enough water to survive. Okay? And this is called semi-arid ecosystems. Semi-arid ecosystems. And if you look there, then how is the vegetation cover in the semi-arid ecosystems? No? And you see things like this. And this is in Namibia, for instance. Which is here is a semi-arid place, okay, between the tropics and okay, there you are. Okay, you see the circles, no? So here, the circles is bare ground, and so the light places. This is no vegetation and vegetation on the other side. Okay, and you see this phenomenon. So here you have just enough water there is just enough water to survive, but if your neighbor take water, you die. No? And you have this instability, and the development of this instability led to the formation of patterns like this. This is a gap pattern. That if you count how many neighbors each circle has, you will see that in average you have 6. So you, for instance, look this guy here, 1, 2, 3, 4, 5. There's a very faint one here, which is 6. Okay? Sometimes it's 7, sometimes it's 5. In average, it's 6. Okay? So we call this an hexagonal pattern. We'll see later why is that. No? So this is an hexagonal pattern of gaps, no? And this is the typical outcome of this instability. And by the way, this in Namibia is what the local people there, the aborigines, called these places where the grass, this is a grass, it's a small, low bushes, something like that. The places where it doesn't grow, they say that was because fairies did something, whatever. No? They call these fairy circles, that's where the name came from. Okay, so that's the name is given in Namibia. And that's why we talk of fairy circles to these patterns. This is not the only possible solution. So this is actually the reducing water, this is the first you get. Homogeneous cover, then you get patterns. If you reduce even more, you get other things. This is in Niger. In Niger, is always semi-arid places between the desert and the equator. No? Here you got stripes instead of gaps. Okay, so this is a plant called tiger bush, and it cannot cover everywhere. They compete and they form these stripes patterns. Okay? So that's as you increase the mortality, less water in this case, you get the stripes patterns. And also sometimes it's stripes, and in the middle of the stripes and next one you have also something which is called labyrinth. So you say something like a labyrinthine pattern. So you keep increasing the rough conditions. And finally, if it is even less water, and it is always in this gap in this region between the semi-arid. No? And here you have the opposite. So here the dark spots are plants. No? And you get these islands of fertility, they are called. So you have these plants here which are spotted. If you look carefully, it is also hexagonal pattern. So the arrangement is hexagonal. No? So you get 6 neighbors in average for every island. No? So you get all so this is commonplace. Okay, so in ecosystems, vegetation ecosystems, as a result of the interaction, they give rise to these patterns. This is an emergent phenomena as a complex system in this sense. So let me go back to the presentation. So the outcome is this. So you see it in the natural setting. You actually see, oops, sorry. You get the formation of these patterns. This is a picture of the Namibia. It looks like this. Okay. This is these gaps here are, I think, is 5-6 meters wide, something like that. And these bushes are this size more or less. And you get these beautiful patterns of vegetation in Namibia. And as I say, you don't see this. You see also the stripes or the spots, a pattern of spots or labyrinthine patterns. Okay, and this is in vegetation, and this has been quite a lot of studied. And the mechanism of interaction is competition for water, essentially. There is also discussions whether termites or other insects may play a role in this. Okay, and that's an open discussion that I'll not go into. So this has been in terrestrial systems. But now I want to talk about the Posidonia. No? And well, in marine ecosystems, spatial structures have been much less studied. The only 2 examples, I think Nuria has some papers on something also. Don't remember exactly. There was a stripes formation by sedimentation or something like that in the delta of. And so there are some works, and here they also in this paper, Barbaroux et al. They see there's also these rings of. I don't remember how exactly it is that the plant is dying because the sulfite is diffusing. And so there is some things like that. And then these gaps in the Posidonia that I was certain it was the same phenomenon. So when I saw those pictures, I knew the studies that were being done in semi-arid ecosystems. So I thought, that's the same. It has to be the same. So these gaps here have to be fairy circles. And that's what they want to explain. Okay? So let's go into that. Then we need a model, and that's what we need. We need a model for the growth of Posidonia. And you know well what we call ABD is for advection, branching, death model for clonal plants. So the basic mechanism of growth of the Posidonia, you know, where is a clonal plant is it has an apex that grows. As it grows, leaves shoots more or less at equidistant distance, at the same distance, is leaving shoots behind as it grows. No? Then you have that, so that's the advection, and you are leaving shoots behind. Okay. Then you have the branching. So with certain rate, omega b, every now and then you branch the apex branch and create a new apex growing forming an angle phi sub b. the angle of branching, which in Posidonia is roughly 45 degrees. Okay? And then on top of that, you have death. With certain rate, shoots and apex die. Okay? So this is creating shoots and creating new apex, and then this is dying. So you have this phenomena, and Thomas Sintes did a model of this, okay, and implemented this in the computer, and it showed like how the shoots would grow, no, and you form a meadow, if you like. So this is a microscopic model, which is fine. They've done several works with this, but the problem with this model is that this microscopic model, you keep track of every shoot, okay, and this is growing exponentially, and after a few times, you have millions and millions and millions of shoots, and that doesn't fit into the computer, okay? So it's not a good model, it's not a good description to study a meadow which is kilometers long, maybe wide. So what we did is, with these same ingredients, we did a model, we derive a model for the densities, okay? So this n sub a is the density of apex and the density of shoots. And so this is the density of apex at position r of the sea bottom, is in 2 dimensions. Position r growing in direction 5 at time t. And the density of shoots at position r at time t. So the variation, that's the spatial derivative, the temporal derivative of this field, so the variation of the density has those ingredients, okay? So that's mortality. So this decreases, omega d is positive, is proportional to the density. So the more density, the more it dies, no? With probability omega d. We assume same mortality for shoots and apex here. Okay? So that's mortality. Then you have the advection. So this term here that has a gradient of the density of apex, and this is the velocity of direction. That's the velocity growing in the direction phi. No? So this takes account of this term of that this apex is growing in that direction. Okay? For all directions, of course. So this is a field. And as this grows, it leaves behind the shoots. So as the apex moves along, it leaves shoots behind. And this is the integral of all directions. So at the point, you have apex growing in all directions, and when they grow, they leave a shoot. That's the number of shoots it leaves there. And finally, that's the branching. So the apex growing in direction phi have a contribution from the apex growing in direction phi plus and minus the branching angle. So those growing in there, when they branch, contribute to this direction here. Okay, so that's the contribution from the branching. And well, that's it. That's it in principle. Okay, and then we have to pay a little bit of attention to the mortality rate. So which is the mortality rate here? Okay, and the mortality rate has several contributions. In general, it depends on the density. Okay, and it has a term that we call it sub-zero that doesn't depend on the density. And this will be the mortality of a single plant. You put a plant of Posidonia in a place, and you have nothing else around, which is the probability that this will die, is this omega d. And this depends on the resources, if it has enough resources or not, also on the environmental conditions. So this is the constant that depends on the environmental conditions. Then you have a term that depends on the density. Okay? And in particular, this term is positive, so if you have the total density, which is the sum of the shoots and the apex, square here, so you have a lot of Posidonia around, that makes you die. It's a saturation term. So this is what sets the maximum density of the meadow. Okay? If you have too much plants, you cannot grow anymore. So as you have more plants around, the mortality increases until you saturate to a certain value. Okay? So that's saturation. And that sets the maximum density of the meadow. And then you have another ingredient here, which is very important, which is the interaction. And that was in the previous works, Thomas didn't include the interaction term. No? Now here we need to include the interaction term because we want to see the pattern. And what is this? This term, what is telling you is that the mortality rate at one point depends on the surroundings, on how many Posidonia you have in a certain range. Okay? And what you are doing here is forget about this exponential, if you like. This is the density of Posidonia you integrate the density of Posidonia weighted with this kernel. And this kernel has two contributions. It has this shape. So it has this, what is it? This is put it is minus k. So this part here is facilitation, okay? This is minus k, so this will be down actually. So this is decreasing the mortality. So you have some plants around, it's good for you, okay? And then it has the other part, which is negative, okay? That increases the mortality. So the plants at a certain distance, in a certain range, compete with you for resources, okay? So in the interaction we are putting in an effective way, we will discuss this later in detail, maybe what can this be for Posidonia. You put in blue facilitation and competition, okay? With two different ranges. So the facilitation, we put it short range, and competition, longer range, okay? And we are putting that because we know that that's the ingredient to having patterns. We can discuss later what this is, if you like. Okay, so that's it. We have the model. In principle, so this equation describes the dynamics of the density of Posidonia. Okay? Many of the parameters are known from your studies, actually. No? So these mortality rates, the velocity of growth, the branching angle, all this we know it from previous study. So we put that in the model already. We don't know what the competition is. This parameter, we set it to get the density we want, which is roughly around 1,000 shoots per meter, no? Something like that. No? So we know this. This depends on environmental conditions. Branching angles and velocities are known, and this is the only thing which is, say, unknown. No? So we have to fit it, or we have to choose what it is. Now, if you study that model, okay, and now we physicists know how to do that, and we find the solutions and the stability of these solutions and so on, you find is this bifurcation diagram. Okay? So what I'm plotting here, this in red, look at the red line first, is the zero solution. This is bare ground. Okay? So no Posidonia, sand. And here I'm plotting the mortality rate versus the branching rate. Okay? So if mortality is much larger than the branching, the only possible solution is bare soil. Okay? Bare ground, no Posidonia. Now, as you decrease the mortality, or increase the branching rate, well, this is equivalent, so the ratio. As you increase the mortality, at certain point, this solution gets unstable. So that's why I put it in dashed, it means unstable. This means that if you have a small amount of Posidonia, this small amount of Posidonia will reproduce faster than it dies, and this will grow. Okay? And if the mortality is very low, you will get an homogeneous cover. You will get an homogeneous Posidonia meadow. Okay? It's this red line. And now, if you study the stability, since we draw it solid here, means because that's stable. So the mortality is very low, means plenty of resources. The homogeneous meadow is stable. Okay? But then, if you are in this branch and you start to increase mortality, at certain point, we have that effect that I explained a few slides before. You get a modulation instability, or a Turing instability. Okay? Which means that because of the competition, if a plant gets some resources here, the plants that are there die because they have not enough. And this gets modulated. And as a result of this modulation, you get the formation of patterns. Okay? And the sequence of patterns you see is the one I said before. So as you are here, this becomes modulated, and the solution, the homogeneous solution, jumps. Here I'm plotting the maximum and the minimum. So the maximum here and the minimum in the gap. The minimum is 0, essentially, so in the middle of the gaps you have 0 density, and close to here you have a density which is higher than the homogeneous. The average density goes down, of course, because the mortality increases. So you get, for instance, when you jump here, you get the yellow line are the gap patterns, which exist in this, are stable in this, for these parameter values. And then you have also the stripe patterns and the spot patterns, hexagonal spot patterns. And in a small system and in ideal conditions, they arrange in an hexagonal manner. That's why we talk about hexagonal patterns. Okay? Well, that's it. So that's what we expect. Well, not only, sorry, one more thing. You realize there are two details here I have not mentioned. That the homogeneous meadow because of the facilitation, that if you have Posidonia helps you to survive, this is biostable. So the meadow can coexist with bare soil, correct? So you have no Posidonia, then it doesn't grow. But if you have a meadow, since they help between them, it may exist. So you have this is the facilitation makes this coexistence, okay? And the competition gives you these patterns. And as you see, the range of the patterns, because of the non-local interaction, when the meadow organized in this fashion, it can survive for much larger mortalities. You see that this extends here. Here you cannot have an homogeneous meadow, but if it organized like that, it's more effective in using the resources. Okay, so this extends farther down, actually. At a certain point, it dies, of course. So that has implications. And the other interesting thing is that these patterns also coexist with the homogeneous solution. So actually, for instance, here you have 3 possible solutions for Posidonia: an hexagonal pattern, or even a stripe pattern, homogeneous meadow, or bare soil. And all are stable solutions, depending on the initial condition, depending on how you set up the meadow, you get that. And moreover, since this pattern is coexisting, the gap pattern coexists with the homogeneous, in this region of coexistence, you have that a single spot, a single gap, is also a solution, and it's stable. Okay? So you can have an homogeneous meadow, but if you make a gap of a certain size, that's stay there forever because of the competition, and that's another solution. And on the other side, you have also a single spot of a certain radius, it's around 20 meters, something like that. That's stable, but it will not grow. It will stay there forever. Correct? You see so that's this is the bifurcation diagram. So that's the prediction of the model. Okay. Let me show you some movies. What time is it? Okay. So this is a simulation starting from that's a homogeneous cover. Okay, that's the density of shoots here around 700, 800. I don't know. We are here, but this is unstable because, as I say, this modulation is unstable. So this will jump and will generate something. Let's see how it does. So it dies somewhere, okay, and in some other places survive. And this starts to compete, and this is dynamic, and notice the timer. Okay, and this forms an hexagonal pattern of gaps in the middle. Okay, and the time scale is realistic because we have put the growth rates, and these are detailed. So this time scale is meaningful. Okay, so this goes very slowly, of course, because it's Posidonia. So these patterns take a lot of time to develop, and its dynamics, you see it moves is very slow, okay, because of the time scale. So that's here. Now if you increase mortality, you keep this initial, now you have this pattern, now you keep increasing mortality, okay, at some point this pattern becomes unstable also, and it jumps to another configuration. So increasing mortality, what you get is this thing. This is stripe patterns, okay. You increase the mortality, the gaps become larger, at a certain point they break down, and you get the formation of stripes. So these are simulations of those equations that Daniel did. You see, over the years, the meadow becomes with stripes. And if you increase even more mortality, what you get is spots. As you increase mortality, the cover is more scarce, so you have less average density, but the plant, if it organizes in this fashion, is more robust, is more resilient. So that's the pattern you see if the mortality increases. Okay? And then you have these other two solutions, which is a gap here. In these mortalities here, you have homogeneous meadow with a gap, or bare ground with a spot. These are also solutions. And this is a transverse cut of the density, of the total density of Posidonia around this structure. If you have any question, just interrupt me, it's no problem. So if you make a cut, so this is the homogeneous density around close to 1,000. Around the ring, you have more density because these plants somehow take advantage of the resources which are free in the middle. So you have more density here. density goes to 0, okay, and you have this circular shape. And this is a cut of there, where you have a bunch of Posidonia here, which is able to live, okay, but cannot expand. Okay, so we think that's the first. We think that this solution here, or the gaps, is this thing in these holes in Cabrera, or those in the Adriatic. Okay, so that's what we did this work. And until here, this was the only evidence we had. It was not a lot. It sort of was a bit weird. And then talking with Nuria told, have a look to the data of the. Well, no, sorry. Before that, then if you look at the satellite images, like I did with Google Earth for the desert, if you do it in the sea, this is Calamillo, well, Calas de Mallorca, yeah, you don't really see anything, because underwater, after a few meters of water, is very dark, and you don't oil, and also the reflection of the sulfur, you don't see much from satellite images. So we don't know if there are patterns here or not. No? And then Nuria told us, have a look to the data of Posidonia meadow, and we went to check the data, so the surveys that you did of the size of the meadows and so on, and that's in the same place. There is this data which is done with the sonar side scans, okay, that have a good resolution of a few 15 centimeters or so of the density of Posidonia. And with this technique, you can see the dark ring is the Posidonia, and the yellow is sand. And you see that, as a matter of fact, in front of Calamillo, you have these gaps here, right? You have gaps. In some places, you have spots, and maybe even a stripe somewhere. Correct? So that was already good evidence. And you have more. Actually, this is not the best picture. This is in front of Calamillo, Calas de Mallorca, and is much more impressive in Pollença Bay. So this in Pollença and Alcúdia Bay as well. If you look at the bay, you look at the meadow is not homogeneous. It's a spot. It's full of spots of gaps. So the yellow is sand. No? So you have gaps in the meadow. You have some stripes as well. You see some lines, and you have some spots. Okay, and this in pink is also Stimulocea nodosa, which has also these patterns. Okay, so we have plenty of evidence, as a matter of fact, that these things is pattern formation. So, I mean, that's the more plausible explanation at this point, we think, for us. So you zoom in, you can see the detail. So you can see, if you count, it's not quite hexagonal. I'll elaborate a little bit later, but it's a pattern of gaps. You see some places it's stripes, and some places it's spots. Or here you have gaps, a pattern of gaps, and a pattern of spots. And they are everywhere. And this summer, so since we did this, we are looking at, and whatever you look around the island, you actually see these things. So this is really commonplace. And, well, it's more zooming in, you see the details. The gaps are 30 meters wide, more or less, in average. Okay? And the distance between gaps is, in average, is 60 meters, more or less. Okay? So that's the pattern. Okay, so with this data, this is a piece of this data. We say, okay, we have a very nice model. Let's try to fit actually the model to the data, and try to get some information. And that's what we did. So we need to introduce a few more ingredients here. And the first was the following. So you have at the bottom, at the sea bottom, you have an homogeneous meadow. And very close to the shore, you have sand. You have no meadow. Okay? So mortality must increase from bottom to the coast. Okay? Somehow. So you have low mortality, large mortality. So that's what we did. We made a simulation, and this is the mortality. And this is the depth. This is the bathymetry. Exactly. So this is just this is -6, all the way to -20-something meters. So that's the bathymetry. And we just we don't know how this is directly related, but we just put a mortality very high here at the top, then a big drop, and then a slow decrease of the mortality as you go to the bottom, such that here you have values which are here, you have homogeneous, here you have values in this transition, okay, and here you have values here where you have no middle. So you put this mortality profile, and as you see, we put also some noise, because the sea bottom will be irregular. okay? And we did a simulation, starting from the homogeneous cover, okay? And that's what you see. After many years of evolution, the Posidonia dies at some places, can live in others, and it starts to form such patterns, okay? And the correspondence is pretty good. Okay, here the only thing we fit, so the only thing we fitted was the parameters of the interaction. So we put an interaction length such that the patterns we get have the same size. Okay, we don't know what that interaction is. Okay, but it's a pretty indirect evidence that here you have this interaction going on. Okay, and as you see here, the similarities are striking. Here you have homogeneous, here you have sun. The intermediate region, you have the gaps, the gap pattern, okay? Even more, because you see that this, here, as you get closer to here, this guy become unstable to this. So the gaps start to become elongated. And you see this also here, okay? Some places. So you get even that. And then very close to at this side, you see that here the gaps are very isolated. And we get that also. And this corresponds to this localized structure. So these isolated gaps that are a stable solution. So you have, because in the sea bottom there is here some defect, the Posidonia dies, and it creates this hole, which is a stable solution of the model. And these are the ones we get here, and look very similar to this. So the similarities are striking. So we think that we are in the good, that we got something here on the Posidonia. So this was the first, so this is a qualitative, let's say, comparison of data and the model. And then the second set of data we checked to compare was this data that Nuria passed us, that these are measures, the blue dots are measures of the density. You can see this very much. Is the density as function of depth. Okay? And these are measures scattered all over the island, no? I understand? Without previous knowledge of the patterns. No? So you have taken measures here and there. Okay? So at the bottom, whenever they measure, they got more or less constant density, correct? But close to the sea, depending on where they measure, they got huge variability. All right? And our interpretation is that this variability depends on which position on the pattern you are. If you are in the middle, you get a very high density. Or when you are close to the rim of the circles, you get a large density. Remember that these circles are 30 meters long, and the walls are 5 or 6 meters. So actually you are there measuring, you don't know if you are in the middle, if you are at the border of one hole, or you are actually inside in the homogeneous region. So by doing that, you get these measures here. So that's a simulation again with a profile of mortality. Then we put also here an extra profile in the parameter B, which was the saturation. The saturation, the parameter B is increasing because the density is lower as you go deep in the sea, no? Because you have less light. So here you have lower densities. No? So that's why we put these two profiles. And we did a simulation. And the gray spots, the gray data here, are densities taken scattered on the pattern. Okay? And what you see is exactly this. Where it is homogeneous, you get the homogeneous value of the density. Okay? And we fitted B to fit this density. And when you get the pattern, you get that if you measure in the middle of one of these spots, you get a very high density. And if you measure at the border, all the densities go all the way to 0. So we think, we don't have exact positions of the data, we could look into that. We think that explains the scatter densities of the measures of the Posidonia. Well, and I'm getting, what time is it? Yes.
When you have a pattern, so you have the maximum density and is used.
Correct.
So why is the experiment you are considering?
Yes. What is the wall? So in the so this is it. This is the density. This is a cut in some direction here. Okay. So here 0. Okay. And if you get one of these spots, you have a high density. Yeah. Okay? And then in the wall, you have all continuous all the way to 0.
Yeah, but the measure of the slope is very thin.
No, well, it looks thin, but it's 5 or 6 meters, because the hole is 30 meters or more. So these walls are actually have some width. So actually, I don't know that, but maybe Nuria, if you go there and start to measure some places, you may very well be at the border of this, no? So the density goes from a high value to 0. No? And in this slope, which is 6 or 5 meters wide, you can measure. You can measure, no? So I believe is that. We don't know. You don't know where you are, no?
So you are doing it like randomly, and then,
Yeah. So as a matter of fact, that's a suggestion I'll launch here. It would be very nice to have. Let me go here. To go in the field, look for one of these holes, and make a detailed measurement. Okay, make a cut like that, and make a number of measurements. You see here the size, no? So these are 100 meters. So this is 1, 2, 3, 4. This is 20 meters. Okay. And the wall, well, you see all this from here to here, you have, I don't know, 5 or 6 meters. So it would be nice in this 5 or 6 meter actually to make measurements in a cut like that, or several, an average, and see whether we do actually see this profile. That would be very nice, for instance. We don't have this data. That's a proposal. Okay. So that's it. So we see these patterns. We have more or less a theoretical explanation for this. And before, to finish, okay, just 2 more slides. I want to focus on the Timescales nodosa, because also the simulations are faster because Timescales grows more rapidly. So, and we see here this nice transition from a pattern of gaps to a pattern of spots, correct? So our interpretation is that here mortality is low, and here for some reason, maybe because there is a torrent here at the right, we don't know, because this is not with depth, it's horizontal, but here the mortality is higher. So you have this pattern. So what we did is, or Daniel did actually, we did a simulation starting from an homogeneous density, but we put here mortality, low mortality, corresponding more or less to this region where you have this pattern. And here we put a high mortality, which corresponds to this region here. Which is high mortality, where this pattern exists. Also bare soil. And we start the simulation, we cover uniformly, and we run the simulation. And look what happened. Okay, first, stop it. Yeah. Stop it. The first thing is that here where the mortality is high, the meadow actually disappears. It dies. Okay? Because we are here, and the homogeneous solution stops here. Okay, so here you have no homogeneous cover, so that dies. And here you have the homogeneous cover, but I think we are actually we are here. No? It's unstable. No? So it starts to form gaps. Let's continue. Yeah? Look at the years. Time scale is slow, although it's Timescales, which is faster. No? So you get the gaps, and after that, okay. The plant is able to colonize that space, but it has to grow in a specific manner, because homogeneously it can't, because there is no homogeneous. But if it grows in this fashion, creating spots and elongating spots and breaking up, is able actually to form a pattern like this. Okay, so you have the plant. Actually, this is a front. No? It's a front of a front moving of this solution over the zero solution, no? And this front is occupying the space, growing in this manner. No? And it actually reproduces the features here. You see that this, how it is, you see, no, what you left behind, some elongated things, and you see how this is actually. So it's very likely actually that this pattern here, it formed like this 1,000 years ago or more, no? Because you need here, the simulation is 5,000 years. No? This is very slow, but it's okay, it's meaningful. No? So that's, it's fiction, if you like, okay, but it's realistic, no? So this could very well be the way it is from some time. Okay, and that's it. Just some conclusions. So I talk about vegetation patterns that I show in terrestrial ecosystems, but that same thing happens in marine ecosystems. We have not talked much about the competition. That in terrestrial is competition for water. Under the sea water is not an issue. So they are competing for something else. Okay? And that's an open question. We don't know what that is exactly. Okay? There are several hypotheses we work with. but we don't know exactly what that is. So that's something is going on. Okay? And then the patterns you get, so when the mortality is close to the critical value, the homogeneous cover becomes unstable, and you get patterns of holes, or failure circles, if you like. And as the mortality increases, you get the stripes and spots. And also these localized structures, which are these isolated gaps. Okay? So you have all these. The ingredient is this long-range competition that we don't know what is, but we are pretty sure that's there. And we need to know which is the mechanism. So actually, the region of the competition is unknown. But we know that the range of interaction from the patterns must be tens of meters, 20 meters, 30 meters, something like that. So that's consistent with the patterns we see. So it has to be there. We need to know what this is. And finally, all this theory that I've explained you more or less nice and interesting, it has also some practical applications. Probably you have already grasped something, no? It has diagnostic power, correct? Because here, if you go here, and you see a pattern like this, you see already more or less which is the mortality conditions. No? And you have the extinction point of the Posidonia will be where this pattern disappears, will be here, at this low mortality. And if you see this, it means that the mortality is already too high for an homogeneous cover to grow. Okay? So if you put here an homogeneous cover, it will disappear. It has to be like that. Okay? So you get this diagnostic power of knowing the conditions of the meadow just looking at the patterns. Okay? It's a bit qualitative, because you don't know exactly which value corresponds, but it's giving you a hint. Okay? So we think that's a useful theory. No? And also, you could also use that, for instance, if you have to design a reforestation project, something like that. This theory also tells you the critical values of the densities above which Posidonia will grow. And they are not here. Here there are some lines, like this one here, of unstable solutions. And this branch here is a separatrix. Densities below this will decay. Densities above this value will grow. Okay? So this also gives you this information. And well, this was published last year, in summer last year, in Science Advances. Okay, you want to look at, and that's what we were trying to explain. And I think that's all. Thank you very much. Sorry, that? Hundreds of years, yeah. Yeah, that's a very good question. You have, for instance, this movie, you have two things here. You have two time scales. There is a time scale of the growth of Posidonia, which is 5 centimeters per year, no? Something like that. So Posidonia cannot grow faster than that. So you have to occupy, well, there is seed dispersal also that could accelerate that. But the apex, the growth of the apex means that this front here, okay, this front here cannot grow faster than 5 centimeters per year. So that's a biological limit, let's say, okay? But then, on top of that, you have the dynamics of the patterns, which introduce another time scale, okay? For instance, if you are close, I don't know if you have ever heard something which is called critical slowing down. It means that if you are close to a transition, for instance, here you have this pattern. Now, here, this pattern is running over the zero solution. Okay? This means because this pattern is actually more favorable than the bare soil. So this front is able to grow. Okay? So the velocity of this front depends on the relativity stability of this solution and zero. Correct? So if this is much more stable, that front will move faster. Maximum velocity is 5 centimeters per year. But if you are to a higher values of the mortality, that front could even move in the other direction. That means that this starts dying and that move in that direction. Okay? And actually, there is a place where that front doesn't move at all. And where it doesn't move at all, the velocity of the growth of that front is zero. Okay? So that can be even slower than this 5 centimeters per year. Okay? So you have a velocity typical of the Posidonia, which is this time scale of 5 centimeters per year. But the dynamics of the patterns can be much slower if you are close to critical points. Okay, so you have these two things, depending on the perimeter you are, if you may be faster or slower. Typically, you see some things like this. Okay, I don't know whether that from velocity here, if you run it again, I don't know if that's 5 centimeters per year or more or less. We have not checked. But yeah, these are real time scales for Posidonia Oceanica. Yeah? So you see, so this is how much? This is meters. Huh? So this is 1.5 kilometers. So this took 5,000 years to cover 1.5 kilometers.
And for the other thing, have you looked into the anthropogenic, some of the anthropogenic impacts beforehand? Because you showed like the anchoring interface. There's lots of spotted areas happen close to the shore and then further away it's not continuous. But we know that Norway is a British shore and preventing age, so that it's happening along the coast where you've got these oceanic and this is what is where the anchoring volume is at the maximum. So this might follow what's already existing in the meadow and create these spots. So it could be anthropogenically driven through the activities we do rather than competition, natural competition.
That's a very good question. We have not looked into that in full detail, okay? But I can tell you something. Let me just 2 minutes. Let's go to Google Maps. Oh, should do it faster. This is what you're talking about, no? I guess. This is Poyensa, no?
Yeah.
And you have all this anchoring, no? Yeah, okay. So it looks very much like what I showed, no? So, so what's my interpretation of this? Here, of course, you have this anchoring. These are fixed anchoring points, I understand, no? So there is a big piece of concrete or whatever, no? And a chain 5 meters long, and then this is moving all the way around, no? So probably these holes you see here, that might be anchoring points, okay? So this would be artificial. This would be, and then you have several possibilities here. Well, this is one thing, okay? So that's one thing. The other is that I don't believe all these things here. Now you can see. I don't believe these are all anchoring points. Would make no sense, no? This is already 20 meters deep, and you cannot have all these anchoring points here, which are fixed. So we believe this is really spontaneous. So the meadow will spontaneously form this, okay? In the region here, it can be what you say. That is possible, no? And then you have several possibilities, actually. If this is happening in a homogeneous meadow, the size of the hole will be exactly the size of the chain, correct? Because the meadow will push in, and where you're right, that will be. If this happens in a place where actually the conditions are such that the plant generates gaps spontaneously, the chain could actually trigger a hole that otherwise, if you are here, the homogeneous is stable, but you have also gaps. So if you have an homogeneous meadow and then you anchor and start a gap artificially, that gap could actually grow to a size which is larger than the chain because of the nonlinear process. Okay? So that could actually be. I don't know the pitch of Poyensa, what that is, because I don't know the conditions there. No? So the answer is, we have not looked into that in detail. The patterns well inside the sea are clearly spontaneous, are not anthropogenic. The ones to the coast can be anthropogenic, but could be amplified by the nonlinear dynamics. Okay? So that could be, but we don't know. Yeah, please.
Yes, thank you for the talk, very interesting. So my question is whether the vegetation patterns ones you presented here on Posidonia are characteristic of monospecific vegetation formation. I mean vegetation.
A single species, you mean?
Single species, exactly.
Yeah. Yes. So what I've done here is I have a single equation for a single species.
Yes, I know, but do you know if the terrestrial examples you show?
The terrestrial examples I show are also single species.
Uh-huh.
Those are also single species.
So do you have an idea about what would happen?
Well, you could very easily, for instance, in the transition with Posidonia and Timodocea, you could very well, you can do that. I don't know if there is any specific reference where this has been done. Probably it is. Okay, here's our model for Posidonia. Okay, you can write the same set of equations for Timodocea nodosa with the parameters specific of Timodocea nodosa, right? And then in the interaction, you can put that the mortality of one plant depends also on the density of the other, and you will get this intra-specific competition, inter-specific competition. So you can model that perfectly. Another issue is which is the value of the parameters of the inter-specific competition. That should be evaluated somehow. But you can do this with this. You can do that with this modeling perfectly. And then you would see, depending on the conditions, if the fronts move one way or the other, or how these patterns, let's say, interact, and all this. Or if you have something which is well mixed or separated or things like that. The model would, in principle, would reproduce that.
Yes, my curiosity is just that the simplicity of the system, because it is only a single species.
Yeah.
It seems that it fosters the generation of this.
Of course.
Maybe in more complex systems, one species could benefit from the
Absolutely. Absolutely.
generated by the other species and
Exactly.
less frequent.
All that will go in here. So that's how the mortality, and here you can put terms that depends on the density of the other species. Then you have to know how to introduce that. If they are competing, or they are mutually beneficial, or whatever, that can be included here naturally. Yes. So the modeling is.
Thank you for your presentation. It was really nice. But I'm wondering what are the hypotheses you have about the resources that might be triggering this mechanism? Because the first thing came to mind for me was nutrient. But for instance, Poyensa Bay is a bay that is highly eutrophied. There is a lot of nutrients going there. So it could be also a kind of anthropogenic pressure. Besides the anchoring, you have all these nutrient inputs that are making the sediment conditions not very good for the growth of Posidonia. So I don't know.
Yeah, we don't know exactly the details on that, but so the nutrient content goes in this mortality here.
Okay.
So that's the mortality rate of a single plant will depend on the nutrient condition. So you are telling me in Poyensa, this is large, so in principle competition for nutrients, well, so that's competition, okay? That affects mortality. And we don't know what this competition is. You are telling me competition for nutrients should not be an issue. Yeah, can be. I don't know. Actually, we don't know what the competition is. No? So we actually, with Nuria and with us, we have discussed several things. No? So one would be direct competition for nutrients through the roots. Another one could be competition for CO2 dissolved in water. I don't know if that's a limiting factor. So which is the limiting factor for the growing Posidonia in Poyensa Bay?
I don't know. I think it's not growing because it's eutrophied, that there is too much nutrients that are worsening the sediment conditions. So that's what I will think
So
in Poyensa, but I really don't know. But
because actually, is the competition in the limiting factor what introduces these patterns? So knowing which is the limiting factor for the growth of the plant there, the competition for that, or the interaction through that, is what would give the patterns. Because that limiting factor is what is driving the system here. No? When you are the limiting factor, you are precisely in this region where you are above.
So it could be oxygen content in the sediment.
It could be oxygen content in the sediment. I don't know.
Okay.
So,
Mm-hmm.
it could be that. So So we have, again, we have introduced the interaction phenomenologically. Can be anything, as we put it here. The interesting thing would be to remove this, and actually here to put a quantity, which could be oxygen, and put another equation for the diffusivity of the oxygen, and see whether that thing will give that rise. Okay, so that could be a thing. Other thing we have to think of is that the plant get poisoned by the sulfites. So it's closer to the oxygen. So sulfide poisoning could be another interaction mechanism, because you have a lot of plants here that decompose, I guess, or no, that could affect that the neighbors do not. And the diffusivity of this thing could give rise to this. Another thing is the hydrodynamics that we have not also. So I mean, the fact that the meadow dissipate the energy of the waves is something that introduces also long-range interaction, because you have Posidonia behind you that shelters you, or I don't know. So globally, the meadow may dissipate differently. You have a pattern or the other. So that is also a possibility. So we have all these things, but we don't know. So actually, we need evidence, and Dan is working on that a little bit. So try to remove this phenomenological interaction and actually put an explicit interaction for a specific quantity, and then put the diffusivity of that quantity and see if that gives rise to the aim or the challenge is to predict the spatial scale. So to put a quantity whose diffusivity explains why these holes are 30 meters and not 5 meters. And that's what we are working on.
Thanks for this very interesting talk.
Thank you.
Yeah, so these holes in the Namibia desert,
Yeah.
read that it was because of termites.
Yeah,
So
that's a huge controversy. Yeah, it's a huge controversy.
termites are there, right?
Yes, they are not in the Posidonia, I guess, no? Yeah, I'm not completely into that, okay? But there are several interpretations, okay? But let me check this one thing. That's an ongoing discussion, yeah. So in Namibia, they claim is that, and you can see this as in two ways. As I see it, and that's my view, but I'm biased, okay? Is that the termites are only are a proxy, so are something that affects the water flow. So there is a coupling between the water, the termites, and the plant. So the termites eat the plant. If the plant dies, there that you have this crust form, and then you have less water income inside. So everything is coupled. Okay. So the termite is an intermediate thing. That's my view. Other people claim no. It's the termites that actually are the termites creating the pattern, and then the plants grow around the termite nest. I don't know. This is huge controversy. Okay. But for instance, you can look at Namibia, but these patterns are everywhere. So for instance, there is another paper, which are very circles. This is in Australia. And in Australia is another group that studies the same phenomena. And this is in Australia, and you have exactly the same pattern, correct? And here there are no termites. So whatever you prefer. In my understanding, the termites are an interaction mechanism that could give rise to formation of patterns as well, besides water, competition for water. But can be other things. And the virtue or the problem of this thing, depending on how you look at it, is that the patterns are very general. Independently of the interaction mechanism, you get the same patterns. Okay? Only the scales may be changed. Okay? So whatever it is that introduces competition, you get this. So it can be many things. So it's difficult to say is the termites, is the water, there are other interpretations also. There is also this toxic substance it's a plant that generates toxic substances. Yeah. So, okay, I don't know details. Okay. So actually we can, and the nice thing would be to translate this discussion into the Posidonia. So what is in Posidonia that is generating black holes? Somebody could say maybe there is a fish that is eating Posidonia, but that thing is discarded. No, so there is no. The amount of animals eating Posidonia is insignificant. No? So that's not a mechanism. So it has to be something else. Yeah?
Thanks for your talk. I wonder if there is a way to know if the time scale is variable. I mean, if you can compare with many years ago, and you can see if the formation of the gaps is accelerating now because of anthropogenic reasons.
How would
Or
you do
not.
that? Yeah, there's no way to know that.
Because maybe in terrestrial ecosystems is easier, but in
Well,
marine
also
ecosystem,
in terrestrial ecosystem, the problem with all this is that the time scales are so long.
yeah.
In any case, that's how you do experiments or how you do checks of that. No? So it's like paleontology. No? So you're looking at evidence of. So I don't think. Well, I don't know how to check that. No.
Or
Ag-
maybe if you have a very strong disturbance in any place, and you can see if these gaps form very quickly or not.
You could do that.
Because
You could kill, but that would be not very
it kept
politically
my
correct.
attention.
But you could kill in a place where you
Still
think
fine.
there is gaps. So if you are in a place where you have coexistence of homogeneous and gaps, you could actually in a homogeneous meadow kill a piece and see how it evolves over the years. For instance, in this experiment, I'm telling you, this is fast. That's fast because the dying is not limited by the 5 centimeters per year. It can die much faster than that.
Exactly.
So the generation of a hole can be actually very fast. Actually, in the simulation, that's fast. Yeah. In the simulations, actually, if you look how the holes form, a little bit carefully, that's fast. Correct. Here, for instance, if you look at time scales, it's here time scales, no? So that's here. So, well, yeah, but this now, you see, so when it decays, that decay is maybe 10 years or 20 years. So if it dies, it goes fast. So that scale is fast. All the others, as I explained, you have the 5 centimeters. So the time scale of the Posidonia is 5 centimeters per year. So that's it.
So you have a restriction.
Yes, and moreover, you have the critical slowing down. So you are close to a critical point, the things will go even slowly than that. So how the gaps, how the patterns evolve, that's very slow. That's very slow. That specific thing of creating a hole, that's fast. You could see if it replenishes or if it grows. No, that would be a test if you are in this narrow perimeter range, for instance. So in this narrow perimeter range here, a gap will grow and will stay at a constant size in the background. These are ideas. Yeah?
Is there any evidence that in the colonization of ambientes from like a volcanic, are these structures being formed also with this?
I don't know. You know any colonization area which is advanced? The only thing I can think of is it was Carlos Duarte suggested that we have to look into that actually. It was in Oyster Bay in Australia that there was a guy that planted, was another species, so make a plantation, and this has been monitored for over 20 or 30 years. So and the plant has been actually growing. The meadow has been growing. So and that there are images every year or every year or every I don't know of how that grows. So we could do that, make a simulation with the parameters of that plant, put the initial condition, and check over the years. No? That could be done. But it's the only set of data I know is this one of Oyster Bay of a replantation, so of a reforestation. No? Naturally occurring, I don't know. More or less, yeah. Yeah, it's realistic, yeah, realistic values there, yeah.
So if this is during the colonization, then instead of going right, we would go
Yes.
towards the left. So I think
It should be.
And maybe for Simodorsia, the pattern we're comes from this other direction of the mortality. Instead of because
So the mortality is decreasing. No?
It's increasing the growth, probably.
So if the plant is colonizing new space, we could simulate that. Yeah, we could simulate that.
And also, I would also to say that the demographic rates are the observed rates nowadays. So actually, in areas that are restored with anthropogenic pressure, they are areas with higher mortality rates. So somehow the anthropogenic pressure is also
Is they are changing this, no?
And what you said about the rapid change in the holes, no? I think it would be interesting to see the time scale of formation of these holes, because these mortality rates that here, the high ones, are recent. It's not that they have, well, I think otherwise, that we have had those high mortality rates for centuries. So, yeah, it would be, I think it would be very interesting to go into this detail of how much time.
Look in the detail of the creation of a gap.
Exactly.
Putting a perturbation and see.
Yes.
So the perturbation again here has a threshold. So
Yeah.
that's a model predict. So here there is a line here in the middle. So if you perturb a little bit, this will grow back. If you would kill above a certain density, this hole will go all the way to zero and will grow to from that. So there is also a threshold. There is a threshold in the perturbation. So we could actually do that. And then, yeah, if you are exactly at the threshold, you have critical slowing down again, and this will be slow. But if you are well above, this will grow very fast. That can be characterized. Yeah. Okay.
Well, thank you very much.
You're welcome. Thanks again.